All right, in this work example, we'll be taking a look at a question which assesses your mastery of the learning outcome associated with the Doppler effect. The question reads, a buzzer emitting sound of frequency 846 hertz is attached to a string and rotated in a horizontal circle. The linear speed of the buzzer is 25.0 meters per second. There you see a little figure with an observer and that buzzer. The speed of sound is given 340 meters per second, and the question is, what is the maximum frequency heard by the observer? All right, so there are times when this observer is going to hear the buzzer at a higher pitch or a higher frequency because the buzzer is speeding towards the observer at a speed of 25 meters per second. Other times we're going to hear a lower pitch because the buzzer is going to be speeding away from the observer at 25 meters per second. And so the linear speed here is sort of like the tangential velocity, right, of this buzzer. That's the velocity of the source. The Doppler effect is the apparent shift in frequency due to the relative motion of an observer and the source of a wave, right? So here we can see the source of the wave is the buzzer, right? The word buzzer is a clue there. 846 is the frequency of the source, right? So we can identify that that's the actual source frequency moving at a speed of 25 meters per second. V in the equation observed frequency equals frequency of the source times V over V plus or minus in general, the velocity of the source. This V is the velocity of the wave. So if it's a light wave that's undergoing the Doppler shift, then it's the speed of light. Here, because it's a sound wave, we use the speed of sound. So 340 meters per second is what we would just call V from this set of variables in this equation. And then the maximum frequency heard, well, that's going to be an observed frequency. And we have to think about, well, we either add or subtract in the denominator, and the maximum frequency is going to be when the source is speeding towards the observer, right? And so that's when we subtract. Towards, subtract, away, add. In order to make the observed frequency maximum, the highest value, we're dividing by the lowest value, right? So that indicates also subtraction. So all of those ideas should sort of be consistent in your mind. All right, so we're going to solve this as 846 hertz, the observed frequency, times the velocity of sound over the velocity of sound. And again, our clue here that we're subtracting in the denominator is that we're solving for the maximum frequency. How do we maximize this observed frequency? By minimizing the divisor here. So that's going to be minus 20. And that does indeed work out to about 913 hertz if you solve it. So choice D is correct there. If you misinterpret the question or you just sort of apply the Doppler effect equation kind of mindlessly without really thinking through it and just like, well, let's just add down there, then you'll get the incorrect value of 788. And so B is the answer that's sort of designed to capture those students that sort of apply the equation, but apply it incorrectly. And I'm not sure about these two answers, but the correct answer is choice D. Moving right along to question number 26, we've got a question which is about the principal regions of the electromagnetic spectrum. The diagram shows the principal regions of the electromagnetic spectrum with some details labeled. The diagram is not to scale. And so they've labeled this region as 10 to the negative 10, and this is region Q, and we have to say what is a typical order of magnitude of the wavelength of the radiation in region Q. Right? The mnemonic device, rowdy Martians invade Venus using X-ray guns, is helpful to remember what the names of these principal radiations are. So we've got from shortest wavelength and increasing the wavelength from right to left, gamma, X-rays, ultraviolet, visible, which we remember Roy G. Biv, right? The different colors of light from the longest wavelength light red to the shortest wavelength light purple. So even shorter than red would be infrared. Microwave is the region that we're sort of concerned with, region Q here. And we just have to know, well, which one's a microwave there? And then radio is the longest wavelength. Knowing that we can see visible light between 700 to 400 nanometers is a nice thing to just sort of anchor your thoughts to. So 700 nano or 400 nano is 10 to the negative 9. So we can remember this as 7 by 10 to the negative 7 meters for red light, 4 by 10 to the negative 7 meters for violet light. And then everything just kind of goes up by orders of 10 there. And so shorter than 10 to the negative 7 would be like 10 to the negative 8. You can see this one 10 to the negative 10, gamma, 10 to the negative 13 or 10 to the negative 16. They get as short as possible. Infrared would be a little bit longer than 10 to the negative 7. So here we have like 10 to the negative 6, 10 to the negative 5, somewhere in there, 10 to the negative 5, 10 to the negative 6. Radio waves sort of go all the way down to about 10 centimeters. And so, 10 to the negative 1. And so microwave would be, 10 to the negative 2. The only answer that's sort of reasonable here for microwave would be 10 to the negative 2 meters, because this one would be infrared, this one would be visible, and this one would be radio. And so none of those are region Q, only choice C, 10 to the negative 2 meters would correspond to that part of the EM spectrum. All right, so make sure that you go through the slides there, and if you don't already have sort of this information down, where you know what all the wavelengths are for the principal radiations, the electromagnetic spectrum, go ahead and get that down in your notes. If you want, for completion's sake, to get all the frequencies down also, you could do that, but it's always calculable if you know the speed of light, right? So all of these are types of light that all travel at this speed related by this. This is the same sort of wave equation for velocity, but it's a special velocity if it's light, right? Very fast, the speed of light. So we'll go ahead and leave this up there for students in class. And if you're watching this on YouTube and you want to get this information down, we'll just pause the video and you can get it down at your leisure. This has been another worked example with Dr. Schleif. We'll see you next time.